gs is equal to 1 over s times s plus 2 s plus 1 to power of 3. Get the gt. How can we do it? First of all, we have to use partial fraction expansion to get easily time domain equation. So gs can be written k0 over s plus k minus 2 divided by s plus 2 plus a1 divided by s plus 1, a2 divided by s plus 1 square plus a3 divided by s plus 1 to power of 3. Okay, let's get k0 s times gs, where s is equal to 0. So it's mean 1 over s plus 2 s plus 1 to power of 3, where s is equal to 0. It will be 0.5 as you see here. Okay, what is the k minus 2? S plus 2 times gs, where s is equal to minus 2. So we can get the original function 1 over minus 2 times minus 1 to power of 3. So we will get 0.5 again. What about the a3 now? a3 is equal to s plus 1 to power of 3 times gs, where s is equal to minus 1. So you can easily see from this function s is equal to minus 1. So minus 1 plus 1, it will be minus 1. What about the a2 now? a2, first derivative of the s plus 1 to power of 3 gs, where s is equal to minus 1. So we have to get the first derivative of the this function. What is this? S plus 1 to power of 3 times 1 over s plus 2 s plus 1 to power of 3. So it can be eliminated as like that. We have to differentiate all this equation. So now we have d over ds 1 over s square plus 2s. Now we can get 0 minus 2s plus 2 divided by s square plus 2s to power of 2. So it's mean minus 2s plus 2 divided by s square plus 2s square. Okay. Then we can get the a2 value now. Minus 2s plus 2 divided by s square 2s square, where s is equal to minus 1. When you put minus 1 into this equation, for the numerator we will get 0. Okay. What about the a3? a3 is equal to 1 over 2 factorial d square ds square and the same function s plus 1 cube and gs, where again s minus 1. We can write this function 1 over 2 d ds we get the first derivative of this function as here. So minus 2s plus 2 divided by s square plus 2s square. Okay, where s is equal to minus 1. So minus 1 over 2. If you get the derivative of this function, 2 times s square 2s minus 2 s square 2s plus 2 and times with 2s plus 2 divided by s square 2s to power of 4 now. Okay, where again s is equal to minus 1. Then we get here, for s is minus 1, you can easily see that here we have a 0, 1 over 2, 2 times 1 minus 2 square divided by 1 minus 1, 4. So you'll get minus 1. Okay, that's all. But sorry about that, we get finally not A3, it should be A1. So we can easily write this function now. What is the K0 value? K0 is 0.5, K minus 2 is 0.5, so 0.5 divided by S plus 0.5 S plus 2 plus, what is the A1? Minus 1 divided by S plus 1. What is the A2 value? It is 0. What is the A3 value? It is minus 1. So minus 1 s plus 1 to power of 3. Now we can transform this function into the time domain easily. How can we do it? You can use the Laplace transform table. 0.5 plus 0.5 e to power of minus 2t minus e to power of minus t. Yes, what about this? Let's look the transform table here. M factorial divided by s plus a m plus 1. By using it, we can convert this. N is here, as you see, 2. So if our function is 2 factorial, it's mean 2, s plus 1 to power of 3. If we have this kind of function, the inverse Laplace transform of it, t to power of 2, a to power of minus t. Okay, but our function is 1 over s plus 1 to power of 3. So we can write t square a to power of minus t divided by 2. Okay, finally we can get gt as like that. Okay, let's continue now. What about the other condition? If gs has simple complex conjugate poles, how can we do it now? Actually, we apply the simple poles rule. There is no any difference between them. For example, if we have S1 and 2 minus sigma plus and minus j omega. Okay, this is the simple complex conjugate poles. We can find the coefficient. Firstly, minus sigma plus j omega is equal to s plus sigma minus j omega times gs, where s is equal to minus sigma plus j omega. It is the same with the simple poles. The other poles can be given as the same way, minus j omega s plus sigma plus j omega times with gs, where s is equal to minus sigma minus j omega. For example, if you take the second order prototype system, gs is equal to omega n square divided by s square to c omega ns plus omega n square. If you know c is less than 1 and greater than 0, we can say s1 and 2 are complex conjugate. So we can represent the same function as k minus sigma minus j omega divided by s plus sigma plus j omega plus k minus sigma plus j omega divided by s plus sigma minus j omega. Okay, what is the sigma and omega here? Sigma is c omega n, and omega is the omega n 1 minus c square. Okay, let's get the coefficient for this function. K minus sigma minus j omega s plus sigma plus j omega times with the gs, which is s plus sigma plus j omega times with the s plus sigma minus j omega, where s is equal to minus sigma minus j omega. Let's continue. We can eliminate this part, as you see here, is equal to, if you put this pole into this, sigma will be eliminated, and minus 1 over, sorry, it is not 1 here, sorry about that, because the function is omega n square, as you know, here. So here we have omega n square divided by 2j omega. What about the other coefficient now? K minus sigma plus j omega is equal to s plus sigma minus j omega times omega n square divided by s plus sigma plus j omega s plus sigma minus j omega, where s is equal to minus sigma plus j omega. It will be eliminated again, and then we get omega n square divided by 2j omega. Okay, now we have this kind of equation for the transfer function. Omega n square divided by 2j omega s plus sigma minus j omega minus omega n square divided by 2j omega divided by s plus sigma plus j omega. If you do inverse Laplace transform for this function, you will get for gt as omega n square divided by 2j omega e to power of minus sigma t e to power of g omega t minus e to power of minus g omega t, where t is greater than equal 0. You can also write this equation by arranging the omega and sigma values as gt is omega n divided by 1 minus kc square root e to power of minus kc omega n t sine omega n 1 minus kc square t. You can easily get this function by using the Laplace transform table again. Yes, as you see here, you can directly get the time equivalent of this function as you see here. Let's continue now. Application of the Laplace transform to the solution of linear ordinary differential equation. This is the new topic now. Let's start from the first order linear system. First order linear system can be written dyt over dt plus a0yt is equal to ft. Ft is the input, yt is the output, and a0 is the real constant, as you know. What about the second order system? Second order system, d square yt divided by dt square plus a1 dyt over dt plus a0 yt is equal to ft. This is the second order system. Yes, linear ordinary differential equations can be solved by the Laplace transform method with the aid of theorems on Laplace transform given before. Partial fraction expansion and table of the Laplace transform, we can use the convert any equation into the time domain. So what is the procedure, general procedure to Laplace transform? The first one, transform of the differential equation to the S domain. How it is possible? By the Laplace transform, of course. Laplace transform using the Laplace transform table. Laplace transform table. It is the first one. What about the other? Manipulate the transformed algebraic equation and obtain the output variable. First of all, we have to convert the function into the Laplace transform, and then we will do some manipulation on this equation. Then perform partial fraction expansion, if you need, of course, to the transformed algebraic equation. Okay, and finally obtain the inverse Laplace transform. Of course, by using the Laplace transform table. All procedure can be summarized as like that. First of all, differential equation should be transformed to the Laplace transform S domain. Then manipulate the transformed algebraic equation and obtain output variable. Then perform partial fraction expansion if you need. Why? Because we need to convert this expression into the time domain. Then obtain the inverse Laplace transform by using the Laplace transform table. For this, let's start from the first order system. 3.4.1 first order prototype system. What is the general form of the first order prototype system? dyt over dt plus 1 over tau yt is equal to 1 over tau ut. What is the tau here? Tau is time constant of the system. What is mean for the tau for us? It is a measure of how fast the system responds to initial condition or external excitation. Okay, it's about the time response of the system. Of course, it is so important. Okay, for this system, let's apply an input to this system. Input is unit step function ut is defined as 0 for t less than 0. Okay, and then 1 if t is greater than and equal to 0. Okay, this is the unit step function. It is very useful input for the analysis of any system. Okay, if you apply this function, ut is equal to tau dyt divided by dt plus yt. And for the Laplace transform, as you know, we have to consider initial condition as 0. So y0 and also dy0 dt should be assumed as 0. We know the Laplace transform of ut for the unit step function is 1 over s. So the same function can be written, this function can be written as 1 over s is equal to tau s ys with 0 initial condition plus ys. So if you get ys parentheses and arrange the equation according to the ys, you will get 1 over s times 1 over tau s plus 1. This is the output in s domain. Okay, how can we represent this in the graphical form? This is the s-plane, real axis and imaginary axis. We have 2 poles for the output, as you see here. One of them is the origin and the other of them minus 1 over tau. And both of them are the real. So, if you get the time response of this system, we have to use again partial fraction expansion. As you see here, first of all, get the Laplace transform of the differential equation. Now we did it. The second one, manipulate the transform algebraic equation and obtain the output variable. Okay, we get it now. And the third one, perform partial fraction expansion to the transformed algebraic equation. Now we will do that. So ys can be written as k0 divided by s plus k minus 1 over tau divided by tau s plus 1. Okay, if you do this operation, you will get k0 as 1 and k minus 1 over tau as minus tau. Okay, we will not do again the same operation. So what is the function for us now? Ys is equal to 1 over s plus, as you see here, according to the coefficients, not plus minus from the tau minus tau divided by tau s plus 1. Maybe we can write this part of this function divided by the tau, so we will get 1 over tau. Okay, it is now very useful for the transform into the time domain. So what is the equivalent of this function now? 1 minus e to power o minus t divided by tau. Okay, that's all. This is the fourth part of the procedure. Now we get the time response of the function. What is the final value if we need? What is the final value of this function? Maybe we can apply final value theorem. Y approaches to infinity, 1 minus e to power o minus t divided by tau. It will be 0, of course. So the total value will be 1. It is the final value of this function. Okay, as the value of time constant tau decreases, the system response approaches faster to the final value. It's important. Maybe I should write, if tau decreases, the system response approaches faster where to the final value, of course. So it's an indicator for us how the system reacts, how it is fast or slow. It is an indicator for us. For this function, if you plot this function, you will get the final value 1, as you know. The time response will be as like that. And what is the tau mean for us? Time constant. It is the 63% of the final value. It is time to need to get to 63% of the system in the time domain yt. Okay, tau means can be given as like that, or the final value, the time needed, for blah blah. Okay, let's continue from the second order prototype system. As we know before, the second order prototype system, d square yt over dt square plus 2 xi omega n dyt dt plus omega n square yt omega n square ut. U is input, y is output for us. Let's apply again. Ut is unit step function, which means us is equal to 1 divided by s. And assume the initial conditions y0 dy0 divided by dt is equal to 0. Then we get ys is equal to 1 over s omega n square divided by s square 2c omega ns plus omega n square. This is the Laplace transform of the function. Okay, what is the characteristic equation of this function? Denominator of this function is set to 0. We get the characteristic equation of this function s square 2c omega ns plus omega n square is equal to 0. Then we get the poles as s1 and s2 minus kc omega n plus and minus j omega n 1 minus kc square. Okay, we have some cases to evaluate this function. If system is critically damped, it means kc is equal to 1. When the roots of characteristic equation are real and equal, then we call the system is critically damped. Actually, we can get it s1 and s2 is equal to kc omega n plus and minus omega n 1 minus kc square. If kc is 1, this part will be 0, so the roots will be minus kc omega n, as you see. Then we get this function as ys is equal to 1 over s omega n square divided by s plus omega n square. So we have a pause, repeated pause, where s is equal to minus omega n. How can we represent in the s-plane the output of the system? We have a pause at origin, and also we have two poles at minus omega n. Okay, we need to partial fraction expansion to get time response easily. K0 divided by s plus a1 divided by s plus omega n, and a2 divided by s plus omega n square. Let's get it. K0 is s times ys, where s is 0. In here we have function. If s is 0, it will be 1, as you see. Okay, what is the a2 value? a2 is equal to s plus omega n square times ys, where s is equal to minus omega n. And if you do this operation, you will get minus omega n. And finally, a1 A1 is equal to d over ds, the first derivative of the s plus omega n square times ys, where s is equal to minus omega n. If you do this operation again, you will get minus 1. So, the completed partial fraction expansion, now you get 1 over s minus 1 over s plus omega n minus 1 over, not my 1 over omega n over s plus omega n square. If you do inverse Laplace for this function, you will get 1 minus e to power of minus omega nt minus t omega n e to power of minus omega nt. Finally, we get this expression. For the second order prototype system and unit step function as input. Okay, what is the other case if the system is overdamped? It means Xi greater than 1. This is the second condition. When two roots of the characteristic equation are distinct and also real, then we call the system as overdamped. So, for such a cases, the same function we have, second order prototype, and unit step function, omega n square divided by s square to xi omega ns plus omega n square. And as you know, S1 and S2 minus xi omega n plus and minus omega n 1 minus xi square. If xi value greater than 1, what will be happen? Sorry, we have a j here. What will be happen? The square root inside of the square root will be minus. So we have a j term, and also we have another j term here. It will be eliminated, and we have real part, only real part. Okay, we have two poles, but each of them has real as 1 and 2 minus and plus omega n xi square minus 1 or minus, yes, as like that. Okay, has only a real part. Let's do an example for this condition, for this case. Let's assume that damping ratio is 3 times square root of 2 divided by 4, and omega n natural frequency is square root of 2. So what will be happen now? Ys will be 1 over s times 2, because omega n square, as you know, s square plus 2 kisi omega n, it will be 3s plus n2. Yes, what is the partial fraction expansion here now? k0s, k1 s plus 1, k minus 1, sorry, k minus 2, s plus 2. As you see here, we have 3 poles. One of them is 0, and the other of them minus 1 and minus 2. Okay, all of them are real. So we can represent it in the S-plane. We have 1, 0 pole, 1, minus 1, and 1, minus 2 poles at the S-plane. Okay, if you do this operation, k0 will be obtained as 1, k minus 1 is obtained as minus 2, and k minus 2 is obtained as 1. Okay, this is the simple pole rule for the partial fraction expansion. So we can represent this function as 1 over s minus 2 over s plus 1 plus 1 over s plus 2. We can easily convert this function into the time domain. Yt is equal to 1 minus 2 e to the power of minus t plus e to the power of minus 2t. That's all. Of course, for t greater than equal. In your books, you have another example. Maybe you should review it. But now, let's talk about this function now. The first term of this function is a constant and gives us steady state. It means in the differential equation, particular solution. Particular solution. What about the other parts? It gives the transient part, and it means in the differential equation homogeneous solution. So if we solve this equation into the differential equation, we have to do particular solution and also homogeneous solution. But by using the Laplace transform, we did all of this operation in one operation, as you see here. Okay, so Laplace transform is so important because of this reason. Okay, maybe we can write it here. Laplace method gives the entire solution, all of this solution in one operation, as you see here. Okay, but if you solve the same equation by using the differential equation, you have to do particular solution and homogeneous solution independently. Okay. Yes, the other condition is system is underdamped, which means Xi less than 1. If system is underdamped, it means Xi is less than 1. Actually not defined exactly, from 0 to 1. So when the roots of characteristic equation are complex with equal negative real parts, then we called the system as underdamped. Okay, underdamped condition satisfied from 0 to 1. Okay, 0 condition or less than 0 is also evaluated. Yes, for this condition, GS has two complex conjugate poles. GS has two complex conjugate poles, S1 and S2, minus Kc omega n, plus and minus J omega n, 1 minus Kc square. As you see here, if Kc is between 0 and 1, this term will be positive. So we have a complex conjugate poles. Okay. If you represent in S-plane for this case, we have, for example, in here a root, and in here the complex conjugate root. And this part, real part of this function, will be Kc omega n, as you see here. This part, imaginary part, will be omega n 1 minus Kc square. So this length of this root will be omega n. Okay, this is the S-plane representation. Of course, sigma and J omega. For this condition, we can write the function as ys is equal to, for the unit step input again, 1 k0 over s plus k minus sigma plus j omega divided by s plus sigma minus j omega plus k minus sigma minus j omega divided by s plus sigma plus j omega. If you get k0, it will be 1, k minus sigma plus j omega, it will be e to power of minus g phi. Phi in the S-plane, phi means, maybe we could represent it here. Phi is angle from 0 to the root. Okay, and this angle can be given as theta. So let's continue now. Divided by 2j square root of 1 minus Kc square, and the other root, final root, k minus sigma minus j omega, it will be minus e to power of minus g phi divided by 2j 1 minus Kc square. Phi can be accepted as the pi minus arc cosine Kc. damping ratio. So the inverse Laplace transform of this function can be given by using the Laplace transform table. 1 minus 1 divided by 1 minus kc square e to power of minus kc omega nt and sine omega n 1 minus kc square t plus arc cosine kc. Okay, this is the time domain response of the function. Let's do an example for this kind of system. D square yt divided by dt plus 34.5 dyt divided by dt plus 1000 yt equal to 1000 ut. Let's examine this question now. For this question, as you know, this part gives us 2 kc omega n and it gives omega n square. Then you can get kc as 0.545 and omega n as 31.622 and 8. Okay. So if you do this conversion, we have here, if you apply this value into the yt expression, you will get 1 minus 1.193 8 power of minus 17.25t sine 26.5t plus 0.993 and 8. It is in radian. Okay, so theta is here. It is theta. Theta is arc cosine kc and it gives 0.9938 radian, and if you write in degrees, you will get 56.94 degrees. If you plot this function into the time domain, as I said before, please remember that this is the steady state part and this is the transient state. So if you plot this function with respect to the time, we will get 1 for the final value and our function will be, maybe I can draw as like that. Okay, this is 1.2 t to yt. Okay, what is the mean of this function now for us? This part gives us a maximum overshoot of this function. Okay, according to the damping ratio, it can be changed. Maybe I can show you on the book, it is more convenient for you. Yes, as you see here, we have this kind of time response, OYT. Yes, according to the damping ratio value, for example, for this drawing, Kc is 0.2. For this one, it will be increased, maybe it can be 0.5. Okay, it should be maybe 0.6. Maybe it can be 0.8. Okay, but as I said before, if Kc value is equal to 1, it is the critically damped. As you see here, critically damped. It means we don't have any overshoot of the system response. Okay, for Kc is equal to 1. If Kc value is greater than 1, as you see here, the system will respond with respect to the time more slowly. Okay, for example, in here, if the Kc value is 2, the steady state value can be obtained for more time. We can represent this function as like that. So let's examine this plane. In this part of the graphic, this part and this part, Kc is between 0 to 1. At this point, Kc is equal to 1. It is critically damped. It means we have only real part. We don't have any imaginary part. If Kc is 0, maybe we can write here Kc omega n plus and minus j omega n 1 minus Kc square. If Kc is 0, it will be here, as you see. The real part of this system will be 0. So we have only imaginary part. The roots will be on imaginary axis. If Kc value is less than 0 and between minus 1, the root will be here, the right half plane or the s-axis, and the system will be unstable. Okay, maybe we can summarize on this. In here, as you see, if Kc value is greater than 1, the system root will be on real axis and the time response will be as like that. If system is critically damped, the system response will be as like that. If damping ratio between 0 to 1, the system has some oscillation and overshoot, and finally we'll get the final value. If Kc is 0, the roots of the system will be on imaginary axis. The system will be marginally stable. Okay, has constant oscillation, and we called as this kind of system marginally stable. If damping ratio less than 0 and greater than minus 1, the system root will be complex conjugate, but real part of it will be positive. It means the system oscillate but increase oscillation. System will be unstable. If we have damping ratio is less than minus 1, the system will be again unstable, is here. We can summarize again here. Kc between 0 to 1, system underdamped. Kc is 1, critically damped. Kc greater than 1, overdamped. Kc is 0, undamped and marginally unstable or stable. Kc is less than 0, negatively damped. It means unstable.